Hello, everyone. Allow me to start by introducing myself. I am Amir Yimer, and today I have the distinct pleasure of presenting my final project for ADTA 5550, Deep Learning with Data, under the esteemed guidance of Dr. Nguyen. In this era of rapid technological advancement, the role of deep learning in data analysis and interpretation is pivotal. My project is an embodiment of this intersection, where I have utilized TensorFlow, an open source software library for machine learning, to address complex data-driven problems. Throughout this course, we have explored various aspects of TensorFlow and Keras, and my project is a testament to the capabilities of TensorFlow specifically. It encompasses the constructions, training, and testing of convolutional neural networks, CNNs, on diverse datasets, showcasing the practical application of these theories. As part of our assignment for ADTA 5550, Deep Learning with Data, we were tasked with the exciting challenge of searching the internet for a dataset in public domain suitable for deep learning research. The task was not just to find any datasets, but to unearth a gem that is both rich in content and diversity, and yet not among the commonly trained classes of dataset like MNIST or CIFAR-10. After an exhaustive search throughout a multitude of resources, including Google Dataset Search, Kaggle, and a repository of awesome public datasets, my quest led me to a remarkable discovery: the Intel Image Classification dataset. Available on Kaggle, this dataset is a treasure trove for anyone interested in machine learning, particularly in the domain of image classification. The Intel Image Classification dataset stands out for its sheer volume and variety. It comprises 25,000 meticulously labeled images, each representing a unique natural scene. These images are not just random snapshots. They are carefully chosen to represent 6 distinct classes: building, forest, glaciers, mountains, seas, and streets. The second phase of my project for ADTA 5550, Deep Learning with Data, involved obtaining and setting up the CIFAR-10 dataset. Step 1. Downloading the dataset. My journey began with the CIFAR-10 dataset, a collection of 60,000 images, each a window into the world of object recognition in computer vision. This dataset, available on Canvas model under the past datasets, is not just a compilation of images, but a well-structured array of visual information divided meticulously into training and test subsets, with 50,000 training images and 10,000 test images. Here is how a dataset appears after clicking the link in the Google Drive module. Downloading this dataset was more than just a transfer of files. It was the first step in bridging the gap between theoretical knowledge and practical application in deep learning. As I navigated through the Canvas interface, I was able to download 7 files and save them in my working directory. The next step was preparing the remote virtual server on the Google Cloud Platform GCP, a modern marvel of cloud computing. Setting up a server on GCP is akin to laying the foundation for a skyscraper. It is the base upon which all our computational tasks would be built. Firstly, let's understand the foundation of our setup: the GCP virtual machine. GCP provides a specialized machine learning image tailored for deep learning application. These images are prepackaged virtual machine image with a deep learning framework ready to be deployed. For our purposes, TensorFlow-equipped images are particularly relevant. Importantly, all GCP deep learning images are based on Debian robust Linux operating system and came with essential pre-installed package like NumPy, Skylearn, SkyPy, and Pandas. An integral feature of this image is the built-in Jupyter Notebook, enabling us to run a server on the remote VM and connect from our local computer, creating a seamless workflow for deep learning projects. Moving on to the G-Cloud SDK, the first step involved authenticating my Google account. This process began with launching the G-Cloud SDK and executing the G-Cloud out login command. Following this, a web interface prompts us to allow access, seamlessly integrating our local environment with GCP's vast cloud resources. Configuring the SSH environment is a crucial setup. Running gcloud compute conf SSH setup the necessary SSH environment. This command leads to creation of the .ssh directory and several key files, including the RSA key files, Google Compute Engine, along with its corresponding private key file .ppk and public key file .pub. GCP automates this process, ensuring a secure and personalized connection to the virtual machine. Step 3. Initiating an SSH session. Now let's focus on the process of initiating an SSH session. This involves specifying the user of the remote instance and the instance itself. The command structure is as follows: $gcloud compute SSH user at instance name project ID zone. Here, the user is typically derived from the Google or Gmail account. The instance name refers to the name of my VM instance. Project ID is my specific project name on the GCP, and zone refers to the geographical zone of the virtual machine. My command was gcloud compute SSH Amir Yimer 2024 at Deep Learning VM projects Amir Yimer data 5550 zone US West 1. Successfully executing this command signifies a successful SSH connection to the instance. This connection is more than just a pathway. It's a secure tunnel through which we can perform various operations on the VM, from file transfers to executing complex deep learning algorithms. SSH is not just a tool, it's a gateway that connects us securely to remote servers. By selecting the Open in Browser window option from the GCP interface, I was essentially unlocking a door to a realm where vast computational power was at my fingertips. Initiating this SSH session took me to the home directory of the remote server, a digital workplace where my CFAR10 database would be uploaded. Step 4. Uploading the dataset. Uploading the CFAR10 dataset to the remote server was a pivotal moment. This process began with a simple command: a beacon in the vast sea of the server's file system, providing us with a clear view of the directory's contents. Then, using the SSH Windows upload functionality, the dataset files previously residing quietly on my local machine embarked on their journey to the cloud. This step was not just about transferring bytes. It was a transfer of potential, the potential to train models, to discover patterns, and to unlock insights that lay hidden within the pixels of this image. Step 5. Verifying the upload. The final step on this process was verification. Running ls-l again in the SSH session was akin to the final check of a complex puzzle, ensuring that each piece was in its rightful place. Seeing the CIFAR10 dataset files listed on the remote servers directory was not just a confirmation of a successful upload, it was a symbol of readiness. It signified that we were now ready to embark on the next phase of our journey, training neural network and diving deep into the realms of machine learning. The genesis of my model's design. The inception of my model's design was guided by a singular aim: to effectively process and interpret the 32 by 32 pixel images of the CIFAR10 dataset, each brimming with diverse features. The structure of my CNN model was meticulously crafted, beginning with the input layer. Here, I declare a placeholder with a dimension of 32 by 32 by 3, encapsulating the height, width, and the three color channels of the image. As I ventured into building the first convolutional layer, I was cognizant of its significance in feature extractions. I employed a 5 by 5 convolution filter with 32 output channels, laying the foundation for the models to capture essential visual cues from the image. The activation function I chose was the recertified linear unit, or ReLU, for its efficiency in introducing nonlinearity, enabling the models to learn complex patterns. Deepening the network's understanding. The journey of an image through the model then progressed to the pooling layer. Here, a 2 by 2 filter with a stride of 2 was utilized, effectively reducing the spatial size and concentrating the feature extracted by the previous convolution layer. This process was not a one-time affair. I replicated it in a second convolution layer, enhancing the depth of feature extraction with a 5 by 5 filter and 64 output channels. Again, ReLU activation played a pivotal role, followed by pooling to further condense the feature representation. The crucial transition to a fully connected network. Transitioning from convolutional layers to fully connected network was a crucial phase. Here, the model's architecture called for reshaping of the 2D features map into a flat vectors, suitable for processing in dense layers. The first fully connected layer was a computational marvel, calculating a dot product of a flattened input with a weight plus a base vector culminating an output size of 1024. Once again, ReLU activation was applied, alongside dropout regularization, to mitigate the risk of overfitting. The final act in my model design was the output layer. This second fully connected layer was where the final logits for each class were produced, with a softmax activation transforming these logits into probabilities. representing the likelihood of each class. Training and testing. Training my CNN model was a rigorous and methodical exercise. Using TensorFlow and Python, I set the model on a course of learning through 5,000 steps. Each step a stride toward understanding and recognizing patterns in the CEFAR-10 dataset. After every 100 steps, I paused to test the model, collecting accuracy data points as a milestone of its learning journey. The testing phase was equally critical. It involved presenting the model with unseen image from the CEFAR-10 dataset, a true test of its learning and generalization capabilities. This phase was not just about measuring accuracy. It was about understanding the model's strengths and identifying areas needing improvement. The results of training and testing the model. The results from my model's training and testing were a testament to its learning capabilities. Starting with an accuracy of just 0.0927, the model showed remarkable progress, reaching an accuracy of 0.6821 by step 4900. This upward trajectory was a clear indicator of the model's ability to learn and adapt. However, this journey is far from over. The results, while promising, also highlight the endless possibilities for further optimization and refinements of the model. The MNIST dataset, a classic in the field of machine learning, comprises simple grayscale images of handwritten digits. It's akin to the first notes of a symphony, introducing us to the worlds of image classification. On the other hand, the CEFAR-10 dataset presents a more complex and colorful array of images, ranging from animals to vehicles, offering a richer and more challenging canvas for our CNN model. When I embarked on this comparative, the analysis initial results were quite interesting. MNIST, with its simpler contents, showcased an astonishingly high accuracy right from the first training step, clocking it over 98%. This rapid attainment of high accuracy underscores the dataset's straightforward nature, making it easier for the CNN model to learn and classify digits. Conversely, CEFAR-10 started with significantly lower accuracy. It was a gradual climb, with a model slowly unrevealing the complexities of the dataset's varied image. This difference in learning trajectory between the two datasets was a fascinating revelation. It highlighted that the CNN model trained on MNIST was more adept at learning and classifying digits as compared to its performance on multifaceted CFAR10. This variance in performance between the two datasets can be attributed to several factors. Firstly, the intrinsic complexity and variability of the datasets play a pivotal role. MNIST grayscale images of handwritten digits are less complex than the color images of various objects in CEFAR10. The latter poses a more demanding challenge for classification due to the diversity in shapes, textures, and colors. Furthermore, the size of the datasets likely contributed to the performance gap. MNIST's larger number of training samples provides a broader base for a model to learn from, as opposed to the slightly smaller training set of CEFAR10. This discrepancy potentially limited the CEFAR-10 model's ability to generalize effectively, thus affecting its accuracy. Additionally, the network architecture tailored for each dataset is crucial. The CNN model for MNIST, optimized for grayscale image classification, may not have been as intricately designed as the one for CFR10, which required more complex architectural consideration and specialized regulation techniques to handle its diverse and colorful image. Let's talk about batch normalization, a technique that has revolutionized the way we train deep neural networks. This method, as described by Garben in 2020, involved standardizing the input value at each layer of the network. What does this mean in simple terms? Essentially, it's like giving the model a more consistent and uniform set of data to learn from at every step of its learning process. The beauty of batch normalization lies in its ability to speed up the training process, allowing the network to learn more effectively. It also makes the model less sensitive to the initial values of the weights, which can be a significant hurdle in training deep network. By implementing batch normalization, I aim to reduce the internal shift that occurs as the data passes through each layer of the network, aligning the output more effectively with the input range of the activation function. The second method I employed was enhanced data augmentation. This approach is all about introducing variability into the training process. I achieved this by applying random transformation, like flipping, rotating, and shifting the image in the training set. The rationale behind this was straightforward. By training the models on a dataset that mirrors a wider range of real-world variation, the model learns to generalize better. This is particularly crucial for a diverse and complex datasets like CFR10. After applying these modifications, the results were somewhat unexpected. In an interesting turn of events, the modified model actually showed a decrease in performance compared to its original version. Initially, the model's accuracy started at 0.0927 and impressively climbed to 0.6821 over 5,000 training steps. However, with the new change, it started at 0.1025 but only reached an accuracy of 0.6216 over the same number of steps. Ladies and gentlemen, I'm honored to present to you my final project report. The heart of this endeavor was to enhance my understanding of constructing and tuning CNNs for image classification tasks. The TensorFlow framework served as our guide and tool in this journey. Throughout this process, I gained essential insights into the underpinning of deep learning, equipping myself with the knowledge necessary to stay abreast of new developments and application in AI. The core of my project involved creating a CNN model within the TensorFlow framework, designed for real-time data analysis and recognition. This model was meticulously aligned with the characteristics of the CIFAR10 dataset. The training and testing process spanned over 5,000 steps, with efficiency checks at every 100 steps. The results of these steps were meticulously recorded, providing a clear view of the model's performance when applied to the CIFAR10 dataset. A critical part of my project was comparing the performance of the CNN on the CIFAR10 dataset within its implementation on the MNIST dataset. This comparison was eye-opening. The MNIST dataset, within its simpler image structure, allowing the CNN to achieve higher performance level exceeding 98% accuracy in the early stages of the training. In contrast, the CNN trained on the more complex CFR10 dataset started with lower accuracy, gradually improving over time. This comparison was vital in understanding how the CNN adapts to different datasets and highlighted areas for further exploration and improvements. Based on observation from the initial phases, I proposed several enhancements to improve the CNN performance on the CIFAR-10 dataset. These include batch normalization to address input variability and data augmentation to introduce a wider range of image variation during training. Unfortunately, these modifications did not yield the expected improvement. The updated model in fact showed a decrease in accuracy compared to its predecessor. This outcome underscored the importance of careful experimentation and evaluation in deep learning model development. Conclusions and future directions from this project. Three key conclusions emerged. Success in training. Part 4 demonstrated that while the CNN model trained on CIFAR-10 showed a good accuracy, there is still potential for future refinement and tuning. Performance variability. The analysis in Part 5 revealed a stark contrast in performance between the CNN models trained on MNIST and CIFAR-10, highlighting the challenge posed by different types of datasets. Complexities of model improvement. Part 6 illustrated that enhancements to the CNN model do not always lead to a better performance, emphasizing the need for meticulously testing and adjustments. In conclusion, this project was a profound exploration into the world of CNNs and TensorFlow. It revealed the nuanced relationship between data quality and model accuracy and highlighted the complexities involved in developing deep learning models. The insight gained from this project paved the way for further research, particularly in improving the CNN models for complex image datasets. Thank you for your attention. This journey through the interactions of CNN and TensorFlow has been both challenging and enlightening, and I look forward to continuing this exploration in the ever-evolving field of artificial intelligence and deep learning.